So in these steps, we will configure the board. We will jumper the GPIO 10 pad to the middle pad here on the solder bridge. You can use GPIO 18 if you want, but you can't choose both. So it's either the center to the left or the center to the right that you have to bridge together. We put in GPIO 18 there just in case you burn out GPIO 10. There have been some reports, some very isolated instances of this happening, and RotorHazard has asked for people who make boards that pull out the GPIO pin to a connector that they add in some redundancy. So that's why we've added that onto this side right here. We will also have the lithium ion cell, the 1220 cell. It's your typical style button cell that you can probably find at the store. We will add that here. And then we will also add in our fan connectors. And the reason why we feel like fan connectors are the best way in this circumstance here so that they can easily be taken off if you happen to permanently attach your fans to the case, which we will do in this video. And then upon maintenance, you can actually unplug them from that side panel so you can easily work on your board a lot better. So the first thing we will do is we will solder the jumper to GPIO 10. So with a nice hot iron, preferably set to like, I don't know, 600 degrees Fahrenheit or 550 degrees Fahrenheit, depending on the solder that you're using, we will solder the two pads together. So this generally just takes not too much effort because there isn't a lot of material here. So we will just solder that, and we will solder that. And with the two together, they're now bridged. So just always make sure there isn't solder also bridging the third one over here. And if you ever want to change these, you can actually just take and you can wipe away some of the solder, either with a solder wick, which is just a copper braided wire, or you can just use your nice clean tip and kind of wick it away. That'll take a lot longer, so if you do happen to do that, do it the more preferred and correct way, which is to use some solder wick. So that part is configured. We will now work on the connection of the fan headers, and there's pretty much only one way that we would want you to do this. This one, it's very apparent which direction, and by the way, these are the like the PH 2.0 connectors that you would find on like Tiny Whoops or your typical toy RC cars. They're very readily available. And these female headers, well, I think these are the male headers because they have the pins on the inside, but they also can come in kits with the actual connector that attaches on them. And what another good thing about these is they're keyed. They can only go one way in, so you can't reverse the polarity and burn out a motor on this. So, but what we typically will tell people is you will take the pin with the key facing towards the holder for your 1220 cell. For fan 1, you will slide that into place. And how you can tell that you've actually done this correctly is it slides in perfectly. If you had this the other way around, this actually doesn't fit. That being said, that does not apply to this other one here. So we will actually take this one, and with the key also facing out, you will put that on here as well. So you'll find out later that we will make sure that the key is appropriately placed using these connectors, because what you can see here is we actually tell you which one is ground and which one is 5 volts. The one closest to the GPIO headers is ground, and the one furthest away is 5 volts. And if you notice that on these pre-made connectors that you can buy like on Amazon, is that the key is in the correct spot, where the red wire is your 5 volts and your ground is your black wire here. So once you get those in place, and typically they'll actually just be in there snug, you can actually just flip this over without it actually falling out. And you can put it down, and then with a bit of solder, you can then connect these together. And how you can always tell you have a good solder joint, especially with this rosin core style solder, is that once it floods over the top of the pin, which remember these ground ones take a little bit of time. There we go. Is that your solder joint is shiny. It means there's very few oxidation that occurs on the solder joint. Now you can see this one's a little bit on the opaque side, but that should be fine. The bottom is really shiny though. So again, we'll come over here. We'll make sure to heat up both pads at once. We'll feed in some solder. We will watch it wick to the pad. And then the 5-volt ones are very quick. There isn't a lot of material for them to heat up. And generally, that just does it very, very fast. Once you're done, always remember to clean the tip of your solder and then pre-tin it to prevent any oxidation while it's still being heated. What you'll also notice on these boards is there's some shield pads. These will later on connect to the cases, and that is to ground the boards to the case to prevent the radiation pattern from your 5.8 receiver or transmitters on whatever vehicle that you're racing from entering certain areas that you don't want. So the next part we will do before we put the cell in is, if you bought the optional BME 280 sensor, we will attach that on now. Typically what we recommend to people is this cell is actually one of the last to go on. We want to make sure that all the components are soldered on because heat is a battery's enemy. And we don't want to affect this battery while we connect these pieces on here. So your BME 280 sensor will come in these bags. You can reuse these if you want to. They're very small, so they're a little hard if you happen to have bigger hands, but they will come with the pin headers themselves. Now how we install it is your actual BME sensor is up on top. It's this silver square pad with a hole in it, and the hole is there for pressure sensitivity. So luckily these are inside cases. Otherwise we would tell you to put a little piece of foam on the top because any sort of air that blows over the top of it actually messes with the pressure sensing of it. So when we do this, we will make sure that the pins are actually down. Now what you can see here is that the pins are actually very long on the bottom. Now, if you wanted to, just like in before, where we cut these pins down to size, you can do that here if you wanted to. However, it's not necessary. What we always want to have ensured, though, is that the smaller pin side, because when these ship to you, one side will be longer than the other. You always want to have the shorter side where the BME 280 sensor is, because you want to make sure there's enough clearance over the top. Because remember, the RotorHazard board will sit over on the top of it along with the Arduinos, and we don't want them to touch each other. So in this case, having the long side down and not cutting them is acceptable, because you can see that the tallest component isn't really these pins. It's actually the headers over here. I mean, even these inductors are actually very tall here, and the 1220 holder actually is pretty tall itself. But in this case, you don't have to. Now, this is the other difficult part. What we suggest is you can either kind of hold it and then push it down on top of the surface, making sure that this is actually a heat resistant pad. If it's not, this is going to burn through your table. So any sort of silicon mat would be nice, or any other piece of metal that you can put on the bottom. But if you don't have anything to hold it, you can use your case or something else to sort of lean it in the right spot. Now, the other thing we'll show you is you can see that the pins can move side to side. When you're ready, you want to be able to make sure that the pin itself is centered, because this will help you when you put the BME sensor on top, because we want to be able to get this parallel with the top of this board over here. So again, with your hot iron, you will tack one of the pins in place. This will ensure that it's in the right spot. Depending on which one you start with, may or may not be the ground one. So we're just going to make sure that's soldered in place. There we go. And it's in the right spot. And now we can take this off. And now it's stuck on there. So now you can get a lot more comfortable with using your soldering iron in place, and you can start tacking the other ones and soldering them. Being sure to be as quick as you possibly can. Depending on the heat setting that you've got, that should be good. And this one's the ground one, so this one's going to take a little bit. So we'll just leave the soldering iron there for just a bit longer. We'll start adding solder so that the heat transfer can go a little faster. We can start getting on the pad. And then we're going to do this one as well. These are right here, the I2C pins for the sensor itself. So once you get all 4 of them done, you just want to check your work to make sure that you've actually connected it. In this case here, you could do a continuity check, but never do the opposites. Always do the ones in line. So all of these ones in line here, these ones on top are 5 volts. The square ones are always going to be ground. And then your SCL and SDA, which are your I2C send and receive pins. Those are the ones on the bottom. But I would only do a continuity check to these ones in line. Don't do cross ones. That may or may not send voltage down the wrong path and may short out some of your components. But if you're fairly certain about your soldering skills and they're pretty well set, we can move on to the next step. Now, this one's gonna be a little challenging, because you can see here its resting state wants to be down. So what we're gonna do is we can take something. It can be anything. In this case, we'll just take an extra set of pins and we will kind of just prop it underneath the board here, just for us to tack it into place. Now, this is sort of a preference thing. You can make it look as pretty as you want, but if it's inside the board area, the periphery, then it's fine. It could be off to the side a little bit. It doesn't really matter. This sensor, we're measuring the ambient temperature over the main power supply of the board itself. So we're just going to quickly tack that into place, and then once that's there, it will actually hold itself, and then now we can come back and we can finish off all the other ones. These ones should go pretty quickly. There isn't a lot of copper on these BME 280 sensors. Even the ground plane would take very little effort to solder. There we go. So, this is starting to become a more populated board. Now again, this is optional. You don't have to have this. For RotorHazard, they've actually taken, there's an onboard temperature sensing unit on the Raspberry Pis, and they've actually adopted it into RotorHazard. So when you turn this on, you'll actually see two temperatures if you have the BME 280 sensor installed. We just recommend that you have this one, even though it's optional, because it'll give you a more accurate reading inside the case. It'll also give you some other weird humidity and pressure sensing if you want it to, but really it's meant for a higher accuracy temperature reading above the main power supply, which is this area right here. Because if you see the temperature rising way too quickly over a very short amount of time, it's possible that you might have a thermal runaway event, aka a possible fire. But we've been testing these boards for entire days, and we have not noticed any rise in temperature, even without the heat sink, the optional heat sink that comes on here. But we do run two 5-volt fans. We misspoke in the previous video. They weren't 20 by 20 fans. They're 30 by 30 fans by either like 10 millimeter thickness. They will blow constant air over the top of the board. Even if your ambient outside temperature is in the summertime, it will keep a good consistent temperature reading. Now, we also left 3 rows of I2C for you to put any other sensors or any other modules, LCD panels, whatever you want. This ensures that not only because this board is a little more universal than the other RotorHazard PCB board, the one that Sleeping Dog Tech sells along with this one, but it also ensures that there's a bit of future proofing later on down the road if RotorHazard happens to implement a LCD panel or any other I2C sensor along the way, even though there is also an I2C breakout over here as well. So now that we've got the board pretty much populated, we can add it to the Raspberry Pi. Now, this can be a little more difficult than the other jobs that we've done so far. But we want to make sure, and also make sure that your pins are straight when you slide it on top. You want to make sure that this board is parallel to the actual power sense board and the Raspberry Pi. If this was off in any way, when you add this to the 3D prints to slide it into the case, it could go very bad. Now luckily, if you notice straight down here, that the fan connector is about the same height as the GPIO pins that are sticking out the back. So you can typically just rest this on top here and it will be pretty parallel. Now you want to check that before you start tacking down your points. With that said, this is pretty much ready to go. Now, in the beginning, we had mentioned that there are circles. The last one over here is a square. These are white lines around the pins that you want to solder into place. There should be on the website a bigger view of which ones to solder, but on the board, on the front and the back, you'll notice that they are circled for you to indicate which ones to do. Because like right down here, there are 2 pins that we do not use. You do not have to solder those. You can, if you want, you can solder as many points as you want, but the way that this is held together, including the hardware that will actually screw everything together, you do not need to solder all of these points. Soldering the minimum required points will actually ensure pretty good mechanical contact between the two boards. So we're just going to go through and we're going to do each one of them one by one. But what we're going to do is, once I attach the one pin here, I'm going to go to the opposite pin, just one over here, and I'm going to solder that one into place. And you may ask why. Now, when you do a tire on your vehicle, like when you actually take it off, and then when you put a new one back on, you do a star pattern. Let me get that on. Yeah, this one's a ground. Come on. There we go. You want to be able to tag these two so that it holds the rest of this board together. Because now, this is pretty solid, even with the 2 points right here. But now I can rest assured that this board is not going to move when I start soldering the other points. Now, besides the ground ones, those take the longest. These other ones, these data lines and the 5-volt line, don't take too much time. So if you've got a nice, good consistently heated iron, and some good solder. I was about to do that one. We don't need to do that one. These shouldn't take too much time. Remember, you're also looking for that nice, shiny finish when you pull it off and it cools down. And if it turns opaque, that's fine. Again, I almost did that one. You don't have to do that one. It's fine, but just know that that could also be an indicator of a cold solder joint. Cold solder joints aren't well, they don't have good adhesion between the two materials that you're trying to bridge together. And sometimes that actually does not let the connection go from one component to the other. And if that happens, sometimes your things won't work. But from years of soldering components together, I'm pretty confident that this is fine. Yeah. Just want enough heat to go down to attach the pins together. Now, I'll point these out again. The ones that you don't have to do are this one up in the corner, closest to the connector, these two here that don't have circles around them, these 6 right here, because those don't have circles. We did cut the pins, but that was to allow you to later on use a desoldering suction pen to take them off without having to run into these pins. Obviously, you could cut them off later on, but we're doing it preemptively. And then these two down here. This one's a ground, and the other one is your LED data line. So that's your GPIO 18. And then your other GPIO 10 is in the cluster up on top. So we're now pretty much halfway done. At this point, you can actually install your lithium ion cell if you want to. You don't have to at this point. You can leave that to the last bit. But what this battery is needed for is this real-time clock, this chip right here, needs power. Now it just sips on it. It's not like constantly going and it's powering like pretty heavy, and you're gonna have to replace these cells, you know, like every day. It just sips enough power that it keeps the clock on the inside going. Now the good thing about the devs on RotorHazard is they've implemented a system where if your timing system did run out of power, which you would just replace this cell on here, the next time you connected the RotorHazard system to the internet, which it could be to your modem or to your hotspot if you're out in the field, it'll actually look online. It will look to see what the actual clock is for the area that you're in. It will change the clock for the Raspberry Pi, and it'll also change the clock for the real-time clock. Now, the RotorHazard timing system uses the real-time clock if you've configured it this way. And the reason why we do this is if you had no internet out on the field and this wasn't powered all the way up to the point where you're racing, if this real-time clock wasn't there, this wouldn't know what time it is. Now, it's not really necessary for races, but if you printed out the sheet that says, oh, at this time this was the heat here, this was the heat there, and this was the heat here, you wouldn't have any sort of timeline as to what time of day that you actually ran that heat. Because with racing, even the time of day could actually affect your race, whether it's the heat on the road that affects your tire adhesion, or the humidity or the dryness of the air while you're flying through it, or even the water that you're moving into. A lot of these things can be helpful in diagnosing if you're going too slow or not, or if you need to train in different environments, or if you needed a different set of tires or propellers. All of these indicators would be very useful to a racer if they knew what time it was. And that's why we have this real-time clock on board, because once you're disconnected from the internet and you're either on a boat or you're on a grassy field or you're in the mountains somewhere, you won't know what time it is. But the real-time clock will always know what time it is, assuming that you have a battery installed and assuming that it is a good battery, not a dead one. So the next steps, once this is pretty much done here, we can put this aside because we will actually be focusing now on the Arduinos, programming them, and the very tedious task of populating all of these pinholes, depending on how many nodes that you're actually planning on doing with pins. Either the pins that are supplied in the kits from the Arduinos that you can see here, or the round pins that we're going to be using for the RX 5808s. But before we start actually populating this board, we're going to jump over to quickly installing the node software, the most up-to-date one on here. We will only need to do this once. And the reason being is, on this board itself, you'll notice that there are UART, TX, and RX lines. Now, for this particular board, has Arduinos on it, and the FTDI adapter that you would actually use to program this, you can still get access to them. However, the devs and some outside devs from another group have created something called RH for RotorHazard -OTA, or over the air. Now, you probably heard about over the air a lot. You get over the air updates for your phone. You get over the air updates for any of your Internet of Things appliances. These are updates that are sent to the different components on the board, which will update them without you actually having to use this board. Now, the reason why we use this board and we flash it with the most current firmware, not only to give you a little bit of a leg up, because, I mean, they just happen to be here, and it's pretty simple to just plug, flash, and plug and flash, but there is a little bit of an issue that even with the first time flashing software on RHOTA, Arduino Pro Minis don't exactly come with pre-installed software. They come with a bootloader, but they don't come with anything on board, which that's what RHOTA requires, is something to be on here to be able to flash to. So what we're going to do is we're going to skip that step. We're going to install the firmware onto here, or the sketch, I should say, since this is programming an AVR chip. And we're going to use this to program it to before we start soldering them on here. But afterwards, you can use that software anytime, and you can update all of them at once. It'll actually reset each of the boards, and it'll flash each of them individually with whatever software happens to be needing updated, because not every RotorHazard update requires you to update the firmware on the boards themselves. Those are rare occurrences that don't happen too often, but luckily with the developers of RotorHazard, you can do that with this board. It's already pre-configured for you. You just have to configure this with the amount of nodes that you have on here. And we'll step that through in the next video. You're going to take your Arduinos and you're going to program the most up-to-date nodes software for the RotorHazard timing system. You can find that on the RotorHazard GitHub page. We'll have links. So this, from here on, this might be just a slight visual, but you can easily just program it using the text manual that we've got online. What we'll show you is when we talked about the unconventional way of programming these, we were actually talking about taking this board and this board and just kind of holding them together. Now, what you'll see here on these FTDI boards is there's a ground, usually a CTS or DTS pin, then your 5 volt or 3.3 volt, your TX, your RX, and your DTR pin. What you will try to do is you will try to match them up. Now, what usually happens is these boards will actually be lined up this way. And you can also see on the back of some of these FTDI boards, the silkscreen will actually tell you what pins are what. So when you look at the Arduino, you'll see you have, they call this BLK, but this is really a ground. You also have your CTS, which is also typically ground on the Pro Minis anyway. Then you'll have VCC, which VCC in this case, in this board, because this is a 5 volt Pro Mini, not a 3.3 volt Mini, you would switch your board over from 3.3 volt to 5 volt, and you would match up that to VCC. And then you'll see that TX, RX are actually switched on the Arduino board. You want that because you want the transmit from the FTDI board to go to the receive of the Arduino, and the transmit of the Arduino to go to the receive of the FTDI chip. And that way they can communicate back and forwards. Just think of it like a regular road for vehicles. And then the last one is DTR. And again, usually on these boards, that's typically ground. Because really all you're going to need are ground, VCC, TX, and RX. Now, the real way of doing this is you would actually solder wires to and from here, and then you would desolder the wires once you're ready to put them on. Now, you don't have to clean out the solder from these holes. The only thing is, if you do it the solder way, because you can see on the actual RotorHazard board here, the one that Sleeping Dog Tech sells, you can see that there's also pins right below it. This is where the chip would actually lay down, and you would notice that if there is solder on the bottom of these and they extend way too far out, you could short them on here. These pads are only meant for the long rectangular ones with the holes through them. They're only meant for the RX 5808s. They are not meant for the Arduinos. So even though you've got a fair decent amount of room between the two different boards, you want to just make sure that it's not overhanging too much, because sometimes if you're a little happy with the solder and you're putting it on, it'll look like it's fine up on top, but it'll keep seeping down underneath it, creating a long glob underneath. So the unconventional way that we have been programming our boards, and a lot of you out there can definitely criticize this. This is not a good way of doing it, but we've seen this done in the past by other people. Is you actually just slide the board on in the right spots, remembering that VCC has to go to the 5 volt, your TX goes to the RX, and your RX goes to the TX. But you'll notice that there's a little bit of slop here. And unfortunately, sometimes if you don't have it in the right spot, you won't provide a good contact. But if you notice on our FTDI board, this pin, or all these pins, are a little bit bent this way, away from the board. And that's because what we do is we put the Arduinos somewhere in the middle, and then when we program the chip, we'll actually take and we'll squeeze this together just ever so slightly. Remember, you don't want to like really grip it together, or else you'll really bend the pins. But what you're doing is you're actually preloading these pins against the pin walls of the Arduino. Now, the reason why we say this is not a great way of doing this is because, one, you're going to fatigue these pins over time if you keep doing this. So if you're doing hundreds and hundreds of these, yeah, this is not the preferred way of doing it. The other way, or the other thing is, this doesn't always provide a good contact. You have to preload it just enough that not only are you not breaking your boards, and you're not breaking the internal connections in here, but you're getting a good enough contact against these pins. And the reason why we do it this way is because you'll contact one side on the back here, but you'll contact the other side on the forward side here. And the second part is, or sorry, the third issue with this is if your finger accidentally touches the wrong thing, you might end up causing a little bit of an issue on the board. These do get a little warm if you keep them on too long. So when we typically do the board, we will insert it in here. We will load up the Arduino software, the Arduino IDE. We will open up the sketch. We will change all the settings. Again, look at the manual online. It'll show you which settings to use for this. We will compile it, making sure that it actually will work. If it throws an error because of memory size, don't worry. It'll fit all onto the board. And then right before we put this on, we'll connect the FTDI connector to our computer, making sure that the 5 volt is turned on. We will slide this into place, and we will preload, and then we will hit the flash button. And it only takes about 20 seconds for it to actually load. And what you can actually see is, if you've done it correctly, there are LEDs on board which will flash very furiously back and forwards when it's actually doing it correctly. Sorry, not the Arduino board, but the FTDI board. There's actually 2 LEDs on either side, and that's actually showing you the RX and the TX line connections. The ones in the zeros going back and forward. 0 obviously being off, 1 being flashing. So this will flash back and forward all the time. If you don't have a good connection, this won't actually flash. The only reason why it flashes is it's transmitting to something and it's receiving information from something. So it does go through send a lot of information to the board, and then it'll receive a lot of information verifying that it's actually flashed correctly. So what you want to just double make sure is, again, enough pressure here that you're not doing any damage to the boards, but you're making good contact here. And this way you can actually cycle through all of your boards at once, because the software is agnostic. It doesn't care that you specify what number node this is. That's why we've actually pre-numbered it into the board. We use a series of grounding pins on these chips, or on these boards right here, and the software will actually determine that this is 1, or this is 5, or this is 8, depending on which position on the board it is. So even if you were to remove one and replace it, if one happens to die in the field, the software will always be like, okay, this position right here is node number 4. So quickly do that, and then when you come back, we will actually start to prepare the pins. We will load them into place. We will put the Arduinos on board, and then we will solder everything on.